Okay, that wasn't even in an epsilon neighborhood of what I said. I have some problems, some of which have existing solutions that are inadequate, some of which don't have existing solutions, and many of which, like 1 or 2, involve cloud computing, but not all of them. The important takeaway, though, is if you have problems you want to bring up, or I'll just sort of warm. That's supposed to be a warm-up for open questions, and then I'm going to turn into the moderator. Okay, if you've seen this talk before, let me recommend the coffee and pastries outside. With an audience that hasn't seen me talk before, I like to start with why I left the university, since many of you are university students or faculty, and why I'm happier and happier having left the university. This is an email I received from the Texas Higher Education Coordinating Committee, which actually runs the entire University of Texas system. Your last name is your password. If you have any questions or you've forgotten your password, please contact the coordinating board. So, having left the university, I thought I would get away from this kind of thing, but here's a form I had to fill out at a previous employer. Type in your name. Notice also the self need not answer the question below. Okay, I'm going to talk about a lot of papers. In this, I'm going to breeze through a bunch of papers. Partly, I'm doing that because I started out with an idea about applying machine learning, and in particular, applying active exploration to make search results or search advertising better, and then just to kind of really encourage you to go for that coffee now. I kind of, in the end, go through a process by which I come full circle and prove, joint with Patrick Hummel, prove a theorem that says everything I thought I was supposed to be doing was wrong. And so, and in fact, now I've gone from being like a strong proponent of active learning to being against active learning. And so that's the thumbnail about what this is about. Okay, so here's the plan. I want to talk about advertising. Thanks to Paul, I don't have to do that very much because I'm mostly going to be talking about display advertising, which he ably introduced. I'll talk about one of the early papers we wrote on this topic, which we call the machine learner's curse, and then I'm going to talk about the value of learning, by which I mean active exploration. So that is to say, trying to bring active exploration into the pricing of the auctions themselves to make it more optimal. Okay. So Paul's already drawn this distinction between performance ads or search ads and display ads. Some estimates hold that display ads are on the order of a $60 billion business. In contrast to Paul's distinction, many of those ads are actually run as performance in the sense that the advertisers only pay when a click occurs. But what's important here is that some are and some aren't, is that there's some of both operating simultaneously. And generally, you rank ads by the probability of a click times the bid. That's a expected impression value. To do that, we have to estimate a click-through rate. And that's where machine learning comes in, big-scale machine learning. And there are, I also want to say that advertisers use a lot of targeting features. So that is to say, it's typically visible to an advertiser. The demographics may be inferred from history, location. Actually, they get me to a set of 4 houses. That is to say, when I go look myself up and say, where is my IP address, it actually narrows it down to 4 houses. It doesn't get me exactly, but pretty close. Interests you can get by time on a web page, characteristics and what time of day, day of the week, and so on are all available. So we're going to estimate the click probability and give this impression value, which is a bid times the probability of a click. And the payment we're going to only focus on second price auction, so this payment is the second highest bid times the click probability for the second highest bid divided by the click probability associated with the highest impression value. As I mentioned, there's lots of targeting, so here's some of the things you might be able to, that people do target on. We maybe have a flash ad that's got a specific size. We know that it's a 45 or between 40 and 45-year-old woman who's in Fort Smith, Arkansas. She's married and has young children, at least judged by the website she visits, which we have in a cookie. We know something about family income, maybe from the demographics. The United States at the 9-digit zip code, we're a very homogeneous country in terms of our demographics, or at least in terms of income. We know some interests, again, judged by websites, what page she's on right at the moment, and what is the day, which happens to be Valentine's Day in this example, and I actually have a picture of her. Here's this woman, she's asked which of the following is the largest, and she picks the elephant over the moon. And this is going to dog her for the rest of her life, and here I am making that worse. One of the things that's really impressive is the way these systems perform. That is the engineering of these. And so in somewhere around a quarter of a second, so you go visit CNN. CNN sends a call to an ad auction site looking for an ad to put on that page. And so there's going to be a call from the page. That call involves passing over characteristics, which are things like the demographics and cookies and so on that we talked about. There may be ad restrictions and so on. All that stuff has to be sent from the web page. And from there, it goes out to the bidders. The bidders, and there can be 40,000 of them, the bidders then have to compute a bid based on all that information. They compute bids. Those bids come back. Click probabilities are then assessed. They may be bidding based on a click or bidding based on an action, such as filling in a web form. So click probabilities have to be estimated for both of those kinds. We need to sort the bids well enough to get the top one and the second highest one, because we're going to second price it. So we need to get both of those. Pull the ad from the database. This, by the way, is the single slowest feature of all of this stuff. Is often what adds time, and when you're sitting there on a web page waiting for an ad to load because they won't show you the content until the ad loads, mostly this is the culprit, is pulling the ad from the database, because the advertisers use some really crummy company. We then send the ad to the web page, and then offline we have to account for the payment and any fees that are associated with it. And then we're going to do all of this stuff and turn around, in some cases, only get $1 per 1,000 ads. That price is a little bit low now. They're a little bit faster. Obviously, what we don't have is a crowdsourced solution where there are a bunch of people in India or Turkey filling these out. Or Ohio, actually, is the median mechanical Turker. So what's the machine learner's curse? Well, here's the thing. We've got a prediction, and that prediction happens with error. They are not error-free. In fact, even after hundreds of thousands of ad runs, you will still have errors associated with the predictions. Well, the fact that we've got predictions and we have the probability of a click in the denominator is already bad, but worse still, when we overpredict, bid times click probability is higher, we're more likely to win the auction. If we underpredict, and specifically if I predict that the click probability is 0, you will lose the auction. If I predict your click probability is 0, if I predict your click probability is high, you'll win the auction. It is the winner's curse. The ads about which we overpredict are more likely to win. And as a result, if I'm pitting an ad that I don't have to make the prediction because it's a payment by impression against an ad where I have to make a prediction, it's a payment by click, I'm going to favor the payments by clicks. That is, I'm going to disadvantage the ads where I didn't have to make a prediction. Worse still, my overpredictions are likely to be, I have more noise in the system when I predict actions versus clicks, that is, actions like filling in a web page or buying something. As a result, the variance tends to be higher on those, and this effect is even more extreme. Now, all of it goes away, right? In principle, as I learn the click probabilities, the machine learning system gets better. It gets measurably better, more or less daily. So in principle, that goes away. This effect goes away. In practice, it does not. And the reason is, over time, old data becomes useless. So we deprecate old data in favor of new data. There are, if I show a movie ad, it'll get a lot of clicks. 3 weeks later, it doesn't get any clicks. The data from the initial clicks gets bad. The amount by which data depreciates is kind of on the order of, let's say, 1 to 5% per day. So goes away pretty quickly. Yes.
So in terms of the statistical problems here, it's not clear to me that, say, unbiased estimators are good or minimizing mean squared error is good. Like, what is the objective, in this application?
Right. So I actually, to fit this in the time, the section I rejected was the loss function section. The loss functions that are chosen, which are either maximum likelihood or squared error, are chosen for convenience. They're not chosen because they actually represent the problem.
The result in the revenue or the, right, maybe it's unclear, right?
Yeah, so there is I have a paper on this, which I'll take offline, which says, joint with Patrick Hummel, which says here's the loss function you should be using for this problem, and to make the estimation better. It's not clear that it actually makes it a lot better, by the way. That is to say, the bad news is that even though it may be optimal, it's actually not that much better. The second thing I'll say is that even with the winner's curse, there's a fix for this. And in principle, we could use the same fix. But the problem here is we need an estimate of the variance. Now, what's the variance of our predictions? And that's a hard thing to know. And the reason it's a hard thing to know is if I do these estimations, let's say with a logistic regression with somewhere between 100 million and a billion right-hand side variables, well, with a billion right-hand side variables, I've got my covariance matrix is a matrix that's a billion by a billion, which is already going to strain your system just storing it, much less computing it. Worse still, I got to invert that matrix. By the way, when we get around to the session on Thursday, remember that. Okay, one thing that every machine learner will tell you is that you should do active learning. That is to say, you should say, I want to actually understand the world I live in. So let me give you the example of, let's say we've corrected the previous problem, the machine learner's curse. We've already corrected that problem. So now I have a bid for an impression of a penny, and I have a price per click ad whose impression value, that's bid times the probability of a click, is also a penny. So it's a dead heat. It's a tie. In that world, I should always pick the price per impression and run that. And the reason is, if I take the impression ad, I don't learn anything. I didn't learn anything at all. I ran the ad. We weren't looking for a click. There wasn't a click. There wasn't any news. There's no news. I run the ad, the price per click ad, and either I get a click or I don't. Either way, that's data. The data goes into the machine learning system. The machine learning system gets better. So I have, in addition to the penny that I expected, assuming I'd fixed the earlier problem, I have I learned something from running that ad. Not very much, tiny amount, but I learned something. So that's what I mean by the value of learning. I should incorporate that into the auction. That is to say, I have this ad which I don't learn anything from, or maybe I've run it. Maybe it's a per-click ad, but I've run it 4 billion times, and so it's AT&T, and so actually they ran 95 million ads in a year, and so I've already run this 95 billion. Sorry. 3 orders of magnitude off, 95 billion ads in 1 year. So I have that ad that I don't learn anything about, and I have this other ad that I've only run once. It's valuable to learn. I would like to incorporate that into the auction. Just that how much I'm going to learn has value. Okay, I want to now give you a different perspective that comes about from thinking about exchanges, which is to say, usually the way machine learners would approach this problem is they'd say, what action should I take? And pick the action. That is to say, it's based on, think of the old style as an array of one-armed bandits, and I'm asking which arm I should take. I want to give a different perspective on that, which is now I have an auction. What I want to ask is, which bid should I submit to that auction? Should I submit how much? So I could just submit the advertiser's bid, or I could perturb the bid. If I don't like this advertiser for one reason, I could decrease their bid. Or if I like them, I could promote them. Very much what Paul talked about with his alpha, I'm going to make it easier or harder for some bidders to win, and that's going to then incorporate the value of learning, the value that the system gets out of learning. So the efficient bid, in fact, is just the immediate value we're going to get plus the value of learning. Think about this in impression space, and then we can do the adjustment on the click to do clicks. Okay, the thing that I didn't take into account at first, and where we're going to end, just there's a saying that you know, if you're a magician and you want to pull a rabbit out of the hat, it isn't very impressive if I show you a hat and they're like ears sticking out to begin with. Okay, this is the ears sticking out. Is that what is different about auctions from the rest of machine learning applications or from other machine learning applications is that the auctions are actually going to give us a fair bit of free exploration. And when we take that into account, the value of exploration is going to be different. Is going to be lower. Okay. One thing that's kind of an aside, but it's something that I got very obsessed with, is that exploring has externalities. And let me just give the example that I've got a Toyota ad, and I've got the website Car and Driver, and I run that, and that's got various features. It's got features like automobile on it, on the page. And if I run that ad, I learn stuff not just about Toyota ads on Car and Driver, but it spills over. So there are externalities. When I go to run a Nissan ad on Road and Track, on the Road and Track website, I've learned something from the other ad. Now, when I'm faced with a problem of externalities, what I might want to do is subsidize the first ad because I'm going to get benefits later. And what you might imagine, and this would be kind of in some sense the optimal thing to do, is to say, let's just keep track of all that. Let's keep track of where we learned and put subsidies in to account for the benefits that we get later in the system. Okay, from a engineering perspective, like that's actually very nice from an economics perspective, and from an engineering perspective, it's madness because it winds up being such a large space, and moreover, it puts me in the position where, let's say I ran this Toyota ad on the Car and Driver website, and what I learned is nobody clicked on it. And then later, I'm thinking about running a Nissan ad on the Road and Track website, and I say, I'm going to charge Road and Track to not run the Nissan ad, and maybe I charge Nissan as well, because I learned earlier that that ad didn't work, or is unlikely to work. That is, I'm going to charge somebody to not do something because I've now learned that it didn't work. Only I'm not going to do anything for them, and so they're going to look at that as being a completely arbitrary and capricious charge. This is a different version of the value of learning. I don't know why that didn't come up. There it is. This is also from Fort Smith, where our woman was before, not literally. You're supposed to do the math here. Arkansas turns out to be the only state in the United States that requires Algebra 2 of its high school students, and now you understand why. Okay. So what this gives us, though, if we're going to try to build in the value of learning, is that when I'm faced with running an ad, I get an immediate value, which has the gobbledygook name, the expected cost per impression, which is actually cost per 1,000 impressions in the actual, the M is actually 1,000, although that would have been K, so I don't know why. But let's say it's cost per impression, it's the expected value. So I have some expected value. Thinking about it as a dynamic program, I'm going to add to that value the value of learning, whatever I expect I will learn from running this ad, which is going to be high on ads that have features I haven't seen very much, so I don't know very much about those features, and it's going to be low on other features. And then I'm going to just second price this animal. So that is to say, I'm going to pick the ad with the highest social value, that's BI, and I'm going to charge a value which is just it's the lowest amount they could bid and still be in the high social value, right? I'm going to second price that animal. And that winds up with the second high, I'm going to charge the second highest value plus the difference in the value of learning. And that's all incentive compatible, and that all works. And you can actually, so one thing that goes wrong with this right off the bat is it could give you negative prices, but we can fix that just by putting a reserve, which is we're never going to pay you to run your ad. We will just zero that out. Okay, so that's the general thought. Now that in itself has the property that sometimes I charge advertisers well, let me put it this way. Initially, I'm probably going to lose money because I'm going to run ads with a high value of learning, and I'm going to have a lower amount. And why should I charge the advertiser that amount? Why should the advertiser be paying? Well, this is this Toyota problem. Is now I'm going to sometimes I'm going sometimes the car driver is going to get less money because there was this negative net value of learning. So sometimes I'm going to give less money to car and driver, and the benefits are going to accrue to somebody else. And what that suggests is, can we split those? Because after all, the value of learning is a social value, not a private value. It's a value to the system, not a value to the individual website. So can I split those apart where I'm going to charge the advertiser the net, the second price of the social value? So that is to say, I'm going to charge the advertiser this amount, but I'm going to pay that amount. That is to say, I'm going to pay the second highest immediate value, and split those apart. We call that a learning account. And so the idea is now I'm going to divorce payments divorce the payments from the amount that I pay out. That is, the advertiser payments from the amount that I pay out. There'll still be a relationship between them, of course, but they won't be necessarily the same thing, because I'm going to pay websites based on what they would get if I ran a greedy auction, and I'm going to charge the advertisers the social second price. And the question then is that does that lose money or not? So let me also say there's another reason why I have to why I might want to divorce these two, which is, if I'm paying websites less money, they may want to say, I'm just not going to take new ads. I'm not going to take ads until I've seen them. You know, I have a vetting process where new ads, which are the ones with high value of learning typically, new ads won't be allowed to run for 6 months. Let somebody else pay the learning costs on the new ads. That can actually make you more money under this system if I'm making the publishers bear the learning costs. And since publishers have a legitimate reason to not run new ads because maybe those ads are obnoxious, and let me prove that, and this is actually something that sometimes really stresses my computer. These are 7 of the 10 most obnoxious ads on the web as judged by Amazon Mechanical Turkers. It's taking a while to get running. And actually this one, what's funny is the Turkers said what they really hate about this ad is, what does a giraffe have to do with mortgage rates? Is that it's just makes no sense. It wasn't that it was like obnoxious like this ad or that ad. It was just that it made no sense. It was irritating because it made no sense. To continue with obnoxious ads, this is one of those ones when you've seen it, it's really hard to kind of unring that bell. It's kind of evil of me, really, to show you that ad. It's like, what were they thinking? Is this really going to sell more pork? But it's the... and then this one is not so much... It's really just bad ad placement. As opposed to the... It's not that it's a bad ad necessarily, but you might see why a publisher says, I don't want to run new ads. There's some bad ads out there, and the fact that there are bad ads out there gives a publisher cover for rejecting new ads, which are the ones where they would get less money. That's a problem resolved by running a learning account where we pay publishers the immediate expected second price, that is what they would have gotten if we followed the greedy strategy, and we run instead instead we charge a different amount, and we hope we make enough money. Now, why should you think that we would make enough money? Well, there's definitely enough money in the system. If we're doing the efficient level of exploration, we're producing more value than we would have without the efficient level of exploration. That's, in some sense, the definition of the efficient level of exploration, is the one that produces the maximum value. So there's enough social resources to pay for this. The question is, can we actually extract them? And what's a fact, not in evidence, is that there's enough in the second price auction, right? In a first price auction where we could see everybody's values, there's automatically, almost by definition, enough value. But in the second price, not so much. Okay, so we're going to pay the publishers the second price. We're going to charge the advertisers the second social value, and then we're going to charge the difference of those things, which, by the way, is not necessarily the same number as this. And the reason is the second highest ECPM, that is immediate value, doesn't have to be the same ad as the second highest social value. And in fact, often won't be. So this, too, is not the same as the second value in the advertisers, unfortunately. Would have been a lot easier if that were true. So then the question is, do we make enough money? Let me actually just illustrate. This is up there mainly because I can do it, rather than any. So what's going on here is there are 4 different ads indicated by their colors. These are their actual expected values. These are the second highest, or the highest social value. So what you see here is, at this point, the blue ad appears to be best. That's because we're overestimating its click probability. And for that, and so the blue ad runs its second price down here. And then at some point we start learning about the blue ad. It dips down below. Actually, it's still running here. Here, all of a sudden, we start running the purple ad. It's dipped down below the purple ad, and we start running the purple ad, and then we learn about that. And this system then second prices. We're going to second price the social value, which looks a lot like upper confidence bound learning. It works very much like upper confidence bound learning. Here's the same thing with lots and lots of ads. This is running 10,000 impressions. This is too slow to watch, so let's just speed it up. And one thing that you see, and actually we can see this here, is these guys almost by definition converge. That is to say, the high value, the social value for the top ad has to be approximately equal to the social value for the second highest ad. Why? Because if they're different, we'll keep running the top ad, and we'll keep learning about it, and the value of learning for that ad will tend to fall until it's equal to the second ad. And because of that, there can be enough money. This is actually the cumulative net learning account. This is a pretty typical picture, even though it's just one run. So it's the run associated with the one I just showed you, which is to say we lose a lot of money initially while we learn a lot. As the learning stabilizes, we start actually making money, and here we're actually making 2%. Now this eventually goes to zero. Eventually, and these, by the way, are the fraction of revenue. So this is 2% of revenue. Notice that we lost 6% of revenue. So here's what I got to with this when we actually completed this work was, do you think we could sell the management on losing 6% so that we'll eventually make money sometime in the future? Any guesses on that? No. Yeah, not even close. And good. Because that turned out not to be the right way to think about it. So let me say, we think of that as actually a solution. By the way, we have a theorem. It's got quite limited. It's got a lot of hypotheses, so it's not that interesting of a theorem that says in the limit you can actually pay for this even in the second price auction. So where we went to next is there are some experiments with active learning. The experiments turn out terribly. I ran one when I was at Yahoo. Actually, we ran this experiment. It was the penultimate launch of Yahoo Search. So that is to say, they had one set of experiments, then they had one more set, which included ours. They had one more set of experiments, and then they outsourced to Microsoft. So we barely got this in. When we run these experiments with active learning to see can we actually make more money by being intentional in our exploration, the answer is typically no. It's either a tiny, tiny amount, like 0.1% or less, or it's even zero or negative. And so these experiments don't typically work that well, and the reason for that turns out to be that when you say how much exploration should there be, the answer is not much. Okay, so let me put this put a little notation up. We've got an ad with an uncertain value. It's got a type that's not observed. We've run it k times. This can all be translated into feature space, but I'm going to tell the story without features to make it simpler. So it's got an uncertain click rate. That's got a mean and a variance. Actually, you're never going to need this notation, but the thing to notice is the variance is divided by, as you'd expect, is divided by the number of impressions you've run it. It's all allowed to evolve with time. This is like the movies, which depreciate over time because people have already seen the ads. Otherwise, we're not worried about time. And we've got some alternative ad that we could run. So that is to say, there's an ad with some distribution, which is our best competing ad, is the setting that we're in. So that gives us a loss function, which is to say, some of the time we run this ad when it's worse than the alternative, and some of the time we run. So if we run the, if we choose a critical value z, some of the time we're going to run this ad when we should have run the other ad. Some of the time we're going to run the other ad when we should have run this ad because we've underestimated it. All of that comes up with a loss function. And so you can now think of, it comes up with a loss function for what the critical value is. So the first thing, which I think we've already seen, I'm going to skip, how much time have I got?
Like 5 minutes.
5 minutes is great. So I'm posing this as a dynamic programming problem, which is to say I'm going to choose the critical value that I use. That is, I'm going to run this ad when the best alternative ad is worse than some critical value z, and otherwise I'm going to run the best alternative ad. So this is the loss function associated with that when the truth of this ad is in this form. That is, it's the mean plus some error, and the critical value I used is z. Right? And so and then what happens when I run that ad is I get this extra kick. I now have run the ad k plus 1 times where I had run it k times, and so that's going to give me an improvement in my value function. And these things are functions of really long arguments that are hidden. And delta is the discount factor. And so this is what our present, the value of the dynamic program turns out to look like. And that's what so that's what I want to maximize, is the maximum value. I want to choose the critical value that maximizes the payoff of the ad, or of running the ad. And that gives me something I pointed out before, but here's the notation for it. The critical value I use is the immediate value I get plus the discounted value of my improvement in the dynamic program. And that this term here is the value of learning. That's the value of learning term in the dynamic program. Okay. What we do then is take limits for relatively large k, and I'll talk a little bit about what happens with smaller k. And the first thing to note is that the value is on the order of 1 over, this value of learning term is at best, of the dynamic program for the value is on the order of 1 over k. And that's just because the variance is 1 over the number of times I've run it. So as a consequence, that difference in the value is on the order of 1 over k squared. Okay, so that is how much I'm increasing my bid to account for the value of learning falls as the square of the number of impressions. How often does that matter? Well, it matters on proportional to the size of the change. So that is, if I increase my bid, most of the time that doesn't make any difference. Some of the time it makes a difference. How often it matters, makes a difference is again also on the order of the square. So that is to say, the efficiency gain associated with using active learning over the greedy strategy falls as the 4th power. It dissipates really quickly. So what this says is, if you compare the greedy strategy against the greedy strategy, mean just maximize whatever is the present value and ignore learning, which is what we do today by and large, against learning, that they converge to each other really quickly. And so instead, if you did something ad hoc, like say, okay, if I've got a new ad, I'm going to explore it 100 times, and then after that I'll just use whatever is the expected value. I'll maximize the immediate value. I'll follow the greedy strategy. You don't go very far wrong, because it's on the order of 1 over 100 to the 4th. Upper confidence bound learning adds a term which is proportional to 1 over the square root. This is the logic is that this is adding a standard deviation term. So I'm going to kick up the value by that. The corollary to the theorem, well, it's not exactly a corollary, it takes more proof, but the optimal value of C is actually 0. That is to say, the greedy strategy beats all of the UCB terms, upper confidence bound learning. So the greedy strategy does a lot better. This is a different kind of greedy strategy. This is list price $8.49. They're charging $10.49, and you save minus $2. We calculate some small sample properties of this. So that is to say, everything I just told you is a limit theorem. We can also calculate small sample properties. Those are kind of complicated, but it comes out if we I'm just going to skip through this. If we calibrate it either to search, and what search, it's kind of a 1% click rate is a pretty normal number, versus display, where the click rate is 1/10. The search click rate, that is to say, it's on the order of 1 in 1,000. And then this is also, I haven't introduced the notation, but this is something that is satisfied empirically, but it also is an assumption. It turns out the gains from active exploration, that is the optimal exploration, are 1/10%. That's actually what's found in practice, or pretty close to it, or 1/1000% for display, which means it's getting that right is almost impossible. Okay, so the main points I want to make, summary. Don't think about what ad to run. Think about what to bid into an exchange. So that is to say, the first thing is pivot the way you think about active exploration from, okay, I'm going to choose the ad. No, you're going to choose what to bid and let the bid determine whether the ad runs. That has an important implication because what it says is explore when it's cheap to explore. Don't explore when it's really expensive. If I've got an ad that's phenomenally valuable and I've got another ad I would like to explore, I shouldn't explore this time. I should wait until some other time. You get a fair bit of a free exploration out of from exchanges. By the way, everything I told you is true about discounting. It turns out if you take the limit as discounting goes to 0, and instead what I do is the maximum, it's the maximum average value, that is the undiscounted value, then the results actually, instead of being k to the 4th, will be k squared. So it's the limit cases are very different in that case. But discounting is a fact of life, so discounting is the right answer to this. Usually, if you're a machine learner and you see a rare feature, you say, aha, let's explore that. Here, the reverse is true. Rare features are bad to explore. Why? Why do I explore rare features? It's because the fact that they're rare means I don't get to learn about them very often. The fact that I don't get to learn about them very often means if I want to learn, that is, if the goal is learning, explore now because you don't get very many chances. Flip that on its head, though, and say, how am I going to use the stuff that I've learned? Well, if it's rare, it's going to be a really long time before I get to use it because it's rare. Doesn't appear very often. As a consequence, what I learn isn't as valuable. You should actually explore the frequent features, not the rare features. The standard fixed exploration period is very close to optimal. This is what everybody uses, and it turns out that's what they should use. And so like I said, this journey for me was to start out saying, this is crazy, only to learn, in fact, this is the right thing to do. And finally, exploration itself may not be worth the effort. Okay, in the specific case of auctions, logistic regression, so I've got parameters on the features. First, only explore negative features. If I've overestimated a feature, if I've got a strongly positive coefficient, it's going to run. It's going to appear in auctions and eventually run. It's only when it's got a negative coefficient that it may never run, in which case I don't actually get to see it in practice. So explore only the negative ones. That cuts in half, by the way, your whole burden of exploration. Explore only when a small boost gets the ad to run. That is, add a little bit, like 5% to those features, and see if that gets them to run. So explore when it's cheap, and sometimes you can do that just with the logs, and do a counterfactual analysis with the logs to say what would have happened. Okay, so the bottom line is exchange context just looks very different from the usual machine learning context, and it gives very different answers. Well, you know you've spoken too long when people quit looking at their watch and start shaking it, only that doesn't matter with this kind of watch. Shaking it doesn't make it work better, whereas taking it off and banging it on the table probably does. And with that, I'm done. Hal?
So there already is a kind of subsidy to new ads because we're comparing the new ads using the features that work for the existing ads. So there's a survivorship bias in the ads you've shown, and here you're treating the new ads on the same basis as those ads.
Yeah, actually, you get what's...
Anyway, the point is, so we are subsidizing the learning a bit.
Right. So that not only that, you get advertisers with really crummy ads leaving the system, changing their name, and coming back as a new ad, and just running them over and over again. And that's true even if you don't learn, I mean, even if you don't have a subsidy for them, that even if all you're doing is saying, I've got a certain amount of ignorance about them that I don't take into account. And so, and at a company I'll remain nameless, but it's not Microsoft and it's not Google. we had salespeople telling advertisers to do this. That is to say, colluding with their advertisers against the company. Other questions?
I have a question, Preston. Yeah, so actually that's the question that I wanted to ask. So to amplify on that, I've heard some ad platforms say that they don't do any explore-exploit trade-off because they're worried about the gaming that would then cause on the advertiser side. So I guess your talk maybe ended up saying that we don't need to do much of it anyway, but
So actually, let me say two things that could be holes that you've brought up. One is there are definitely advertisers themselves doing a certain amount of exploration, right. And they can do that by the same mechanism I just described of increasing their bid. And you see, especially advertisers who have contracted with search engine managers to help them, doing a lot of active exploration. That is, moving their bids daily throughout the day, where 80% will be at a certain price for a given ad, and the other 20% will vary a fair bit. So they seem to be doing. So there's a lot of also free exploration that we've just set aside. We've made the advertisers passive in this process. But the advertisers themselves have an incentive to do it. On the other point that you made, I've heard this point. I don't actually, and I agree, active exploration makes that point worse. But if I'm only doing a little bit of active exploration, first, that exists even under the greedy strategy. That is to say, advertisers might game the system in the way that I already mentioned, which is if your ad doesn't perform very well, leave the system and come back in as a new advertiser. This makes that slightly worse, right? But that already exists. The techniques used to stop it, which is to basically recognize the advertiser and stop them from doing this, which, by the way, can be as simple as using, is this the same credit card? Because they're often small advertisers, and they don't have access to a whole lot of credit cards. That problem exists. We make it a little bit worse, but it's just marginally worse. So I don't think of that as being too serious a problem. Whereas I think of the fact that the advertisers are doing their own exploration, it may be that there's really no reason to do any exploration, that you're getting enough from the advertisers themselves. And that's an overwhelming advantage.
So this is a slightly different dimension, but related, and you mentioned that, so one issue is how much of the value you can extract from the advertisers, and so you don't probably really think that they have serially uncorrelated values for every auction, and so if they have persistent values, you might want to use some kind of dynamic mechanism where you are extracting something up front because you really screen them based on the initial information. So you said, is there a reason? And that will help a little bit for the experimentation problem as well. So why wouldn't that be used?
Right. So let me agree that I think it's not used just because it's complicated, and we don't have what I think of as clear direction of what we should be doing dynamically. I completely agree that so when they do these predictions, you actually have advertiser-specific effects. So if it's a automobile ad or a lipstick ad or whatever, there are characteristics of the ad. You have characteristics of the page it's on. It could be a news page or a movie page or what have you. And then you also have characteristics of the user. So the user can be male or female and so on. All three of those go in. The one that's can be reasonably viewed as independent across time is probably the user characteristics. But even then, there might be some correlation. But those might be reasonably independent. Many of the other features that you're learning about are almost surely correlated, especially at the ad level. So that is, in particular, if I look at a specific ad, a Toyota ad, it's the advertisers it's up against will be correlated with the ad characteristics itself. By the way, the theory allows for that. That isn't a problem for the theory, because the theory starts with a Toyota ad and just says the other advertisers are a draw, but they could be correlated with the Toyota ad. That's not ruled out. They are treated as independent of each other. Actually, that's not even necessary, because all we need is the distribution of the best one. But it needs to be random. There needs to be some randomness. There may not be, or not be very much, in which case that would be a defect of the theory. If you've got a pointer to something that tells me how to do better dynamics, I'm actually pretty interested in it. I haven't really been following that literature recently. Okay. Thank you.